We are meticulously deconstructing the high-voltage circuit breaker maintenance process inside an active substation, revealing the intricate steps involved in ensuring grid stability and safety. This involves isolating, de-energizing, and systematically inspecting critical components, highlighting the precision required to handle immense electrical forces. Upon entering the substation, the first priority is establishing a safe work zone, a procedure governed by stringent protocols. Our team begins by isolating the specific circuit breaker from the rest of the electrical grid. This is not a simple flip of a switch. It involves coordinating with the grid control center to reroute power, ensuring that the disconnection of this single component does not disrupt the flow of electricity to thousands of homes and businesses. Visible air brake disconnect switches are opened on both sides of the breaker, creating a physical gap in the circuit. This visible isolation is a critical safety measure, providing an unambiguous confirmation that the breaker is no longer part of the live, energized network. Once the disconnects are open, they are locked and tagged out, a procedure known as LOTO lockout tagout. Each technician involved places their personal lock on the switch, guaranteeing it cannot be re-energized until every individual has completed their work and removed their lock. This foundational step of isolation is paramount, transforming a zone of immense electrical potential into a controlled environment where detailed work can commence. The air crackles with a latent energy, a constant reminder of the power held at bay just meters away, underscoring the gravity and precision of every action taken. With the circuit breaker electrically isolated, the next crucial phase is de-energization and grounding. Although disconnected from the grid, components like bushings and internal capacitors can retain a dangerous electrical charge, similar to a static shock, but on a lethal scale. To neutralize this residual energy, a portable grounding assembly is carefully applied. This device consists of heavy-gauge copper cables connected to a certified grounding point, typically a copper rod driven deep into the earth or the station's ground grid. Using an insulated tool known as a hot stick, technician first tests for the absence of voltage with a specialized detector. After confirming zero voltage, the grounding clamps are securely attached to the terminals of the circuit breaker. This action effectively creates a short circuit to the ground, providing a safe path for any stray or induced voltage to dissipate harmlessly. It ensures that the equipment is at the same electrical potential as the earth, making it safe to touch and work on. This grounding process is a non-negotiable step, a deliberate and methodical ritual that stands as the final barrier between the technician and the lethal potential of stored energy, allowing the physical inspection and maintenance to begin with the highest degree of confidence in the safety of the work area. The silence that follows the final click of the grounding clamp is profound, marking the moment the giant piece of machinery is truly rendered inert and ready for human hands. Now that the circuit breaker is fully isolated, de-energized, and grounded, the systematic inspection of its critical components can begin. The process is a meticulous top-to-bottom examination, starting with the external structures. We inspect the porcelain or polymer bushings for any signs of physical damage, such as cracks, chips, or contamination. These insulators are vital for preventing electricity from arcing to the grounded metal structure of the breaker, and even a small flaw could lead to a catastrophic failure under high-voltage stress. We look for traces of corona discharge, a faint violet glow that indicates electrical stress breaking down the surrounding air, which can degrade insulating materials over time. The integrity of all gaskets and seals is checked to ensure they are preventing moisture and contaminants from entering the internal mechanisms, as ingress of water can compromise the insulating properties of the gas or oil within. Following the external check, attention turns to the operating mechanism, the powerful heart of the breaker. This is the system of springs, compressed air, or hydraulic fluid that provides the immense force needed to open or close the breaker contacts in milliseconds. We examine hydraulic lines for leaks, check compressed air systems for proper pressure, and test the tension of closing and tripping springs. Every linkage, pin, and pivot point is scrutinized for wear and proper lubrication, ensuring that the mechanism can respond instantaneously when called upon by the protective relays. The inspection then moves to the very core of the circuit breaker, the interrupter assembly, which is the component responsible for extinguishing the powerful electric arc created when the circuit is broken. Depending on the type of breaker, This involves different procedures. For a sulfur hexafluoride SF6 gas breaker, which is common in modern substations, the first step is to analyze the gas itself. A small sample is drawn and tested for purity, moisture content, and the presence of decomposition byproducts. SF6 is an excellent insulating and arc-quenching medium, but its effectiveness degrades if it becomes contaminated. Low gas pressure or high moisture levels can severely impair the breaker's ability to interrupt fault currents, so the gas may need to be filtered or topped up. We then perform a series of diagnostic tests without opening the main tank. A travel analysis, or timing test, measures the speed and synchronization of the moving contacts. The contacts must separate and close within a precise time frame, typically a few cycles of the AC waveform, to ensure the arc is extinguished at the optimal moment, the zero crossing of the current. A slow-moving contact can result in a prolonged arc, causing severe damage to the interrupter and potentially leading to a violent failure. Another key diagnostic is the contact resistance measurement. A low-voltage, high-current signal is passed through the closed contacts, and the resistance is measured. An elevated resistance indicates pitting, corrosion, or misalignment of the contacts, which can cause overheating and energy loss during normal operation. Finally, we delve into the auxiliary systems that support the breaker's operation. The control cabinet, the breaker's brain, is opened, and all wiring is inspected for tight connections and signs of overheating. Protective relays and control circuits are tested to ensure they send the correct trip and close signals to the operating mechanism. The heaters within the cabinet are checked to confirm they are functioning correctly, as they prevent condensation that could corrode electrical components or cause short circuits. The battery system that provides backup DC power to the control and trip circuits is also thoroughly tested. This system must be capable of operating the breaker even if the station SAC power is lost during a fault, making its reliability absolutely critical. Every terminal, fuse, and indicator light is verified. This comprehensive, multifaceted inspection ensures that not just the primary function, but the entire ecosystem of the circuit breaker is in perfect working order. This highlights the precision required to handle immense electrical forces, ensuring the breaker stands ready to protect the grid from faults and maintain the stability of our power supply.